Okay, if we move on to 30b here, we can see that this is going to be an ellipse because we have two positive terms here. The first thing we have to do, though, is get this thing into standard form. We're going to do that by, remember, this term's got to be a 1, so we're going to do that by dividing by 36. And then when we simplify that over here, we get some cancellations on the top. We have x minus 1 squared over 4. 9 divided by 36 is 4. And then we get y plus 1 squared over 9 equals 1. So from this we can, to get our sketch, we need to get a and b. We can see that this is going to be a north-south oriented ellipse because the major radius is the bigger number under the y term. So a squared will be 9, leaving us with a equals 3. That's going to be our major radius. And then we have b squared equals 4, which gives us b equals 2. And then we also need to get c squared, and for the ellipse, remember our equation is a squared equals b squared plus c squared. And again, the foci are inside the ellipse. That's how I remember that the a squared has to be the biggest term because a is the major, and so c is smaller than it. Then now we have everything we need to get there. A squared is 9, b squared is 4, plus c squared equals 5. So c is going to be root 5. We can glean our center off of here. The center is going to be just 1, negative 1. And let's go ahead and sketch. Do this in red. Center is going to be 1, negative 1, so we're down here for the center. And then to get our major radius, we have to count up 3 from there because we know it's north-south, so 1, 2, 3. That's going to be our vertex 1. Go down 3 to get the other vertex. 1, 2, 3. That's vertex 2. Then our major radius is 2, so we're just going to count off to the right 2 spots. 1, 2. 1, 2. And we called those the co-vertex. We could just label them here if we wanted. Now we can just connect the dots to get our ellipse. Wow, that's not very good. It's hard to do on a tablet. So that's our sketch, and then we just also need to get, if we were actually going to write the coordinates of the vertices out here, we could do that. The center, the y coordinate of the center is going to be negative 1, and we're going to add and subtract 3. So that's one way to do this here, is just negative 1 plus or minus 3. We know the y coordinate, sorry, the x coordinate is 1. And then to get the foci, we can do a similar thing. We need to get here, and we're going to go up root 5. So the foci are about right here. Those in green. Let's focus 1. A little over 2 here. Focus 2. Remember what those foci mean, right? If we had the string here, we could connect the string, and it would, that sum of those two distances is a constant. That's the definition of an ellipse. And to get the foci here, we're going to take, again, the x coordinate is going to always be 1 for these foci, and then we're going to take our center, negative 1, and we're going to add and subtract root 5 to get our foci. So I think that's all the parts of our ellipse and the sketch. So number 31 here, this is our standard write the equation of a conic type problem given some information. We have an hyperbola. So the thing I always like to do on these guys first actually is just make a really quick sketch to see what's going on here. So let's just do that. The vertices are at 4, 0. So 1, 2, 3, 4. 4, 0 is the one vertex. And 4, 4 would be kind of up here. So right away we know this thing has to kind of look like this. Right? We don't know exactly what the asymptotes are. We have an equation of one, but so we know it's going to be a north-south hyperbola. So I'm going to go ahead and write. We know that that's going to be x minus k squared over a squared. And now we know that this box, whatever it's going to be, the major radius has to go under the y, so we know a is going to go there. We have x minus h squared over b squared equals 1. So what information do we have here? Well, we know that the center has to be between the two vertices. So right there, we're given our center is going to be, we know it's going to be 4, 2. So we have k, we have h. we know the distance from the center up to this vertex. It has to be 2. Right? We're at 4, 2 here. We're going up to 4, 4. That's going to have to be 2. So we know that a squared, a equals 2, a squared equals 4. So the only missing piece here is b. We don't really know b squared. So how can we use this asymptote to figure out what b is? Well, remember that the asymptote has to go through the corner of the box. And so we know the corners of the box in this, so we can use the slope of the asymptote to figure out the relative values of a and b. So if I rewrite the equation of the asymptote in slope-intercept form, just so we can easily see the slope, it's y equals negative 2x plus 10. So the slope of the asymptote has to be negative 2, so we know that's rise over run in this box has to be, well, this one would be the negative 2 one, but we can just use it as 2. It's not really so important. So the rise in this box, since it's a north-south hyperbola, rise over run is, you can think of it as the ry over the rx radius. That's the terminology we used. Or in this case, it's going to be a over b. And we know that that has to equal 2. So now we can use our information. We have a equals 2, so 2 over b equals 2. And solve that to get that b must be 1. So now we have everything we need to finish this off. I'm going to finish it off in green down here. We have y minus, now make sure you use the y coordinate here, k. So y minus 2 squared all over 2 squared, which is a squared. X minus 4 squared, that's the other coordinate of the center, the 4. And b squared, we've just solved for b, is 1 squared equals 1. So the key here is just to always remember that the slope of the asymptote gives you information you need about a and b, because we know that in our hyperbola box, this dimension here is a, and this dimension here is b. So here we're going to, number 32 in the problem packet, we're going to write the equation of an ellipse this time. And my preferred approach here is start off with making a quick little sketch. Center at negative 1 and 2. Negative 1, 2, so negative 1. We know the center of our ellipse would be here. We have a focus at 0, 2, so 0, 2. That would be our focus. And the vertex at 2, 2. 1, 2, vertex. So if we wanted to sketch this thing in here, we already can see that it's going to look something like this. Right? The center and the focus is inside the vertex, so it looks like we have some good information. We know that it's going to be a east-west ellipse because the vertices always tell us which direction it's going to go. So we know that this is oriented this way. So it's going to be an east-west ellipse. Okay, so let's go ahead and just write this. We have the center as negative 1 and 2. So our standard form of the ellipse equation will be x minus h squared plus y minus k squared. That's all going to equal 1. In this case, since it's east-west, a squared has to go under the x term, b squared has to go under the y term. We have a here, the distance between the center and the vertex. Just gotta, all you just get to get that, just count over. We're at negative 1, 2, 3, so a is going to be 3. And it's the same, just like the last problem. We don't know what b squared is. We have to use some other information. So to get that, we have to use, but we do know the focus here. So if we count off to the focus, negative 1 to 0, we know that c actually is 1 here, because the distance from, trying to show that in green, from center to the focus is 1 unit. So we know c equals 1. So then we can use the relationship for an ellipse. A squared equals b squared plus c squared. We have 9 equals b squared plus 1 squared. B squared equals 8. Since I need b squared, I'm not even going to bother taking the square root of this to get b. Now I think we're armed with everything we have, or everything we need to solve this problem. X minus h It's going to be plus 1 because we have the x-coordinate of the center. A squared here is 3, so we're going to do 3 squared plus y minus k. The y-coordinate of the center is 2, so we subtract 2 here. We've solved for b squared here, which is 8 equals 1. And just to make this look nice and uniform, I'm going to change that to a 9, 3 squared. And that would be the equation of this ellipse. Number 33, this is just a pretty straightforward problem. Name the conic sections, but we can just talk quickly through, again, where they come from. The first one I'm going to mention here is parabola. And I'm going to put that with its degenerate counterpoint, the line. Remember, when a parabola degenerates to a line when that slicing plane starts to hug the edge of the cone. And yeah, we remember about the cone here. Where does the parabola come from? Well, it's when we slice the cone exactly parallel to the side. And then that traces out this parabola in there. And then the degenerate one will occur when the slice occurs exactly at this. If we keep moving this plane this direction, it would get to the side and create the line. The second set is the ellipse. And the degenerate version of that is just a point. And let's recall how we get the ellipse when we cut the cone. Well, it's when the slicing plane is less steep than the side. And then we get this ellipse that gets cut through there. And then when the slicing plane passes through the vertex, just like this line, when it passed through the vertex, that's when you get the point. So that would be if the slice occurred up here, that would give you the point. Our third one is the hyperbola, and its degenerate counterpart, which is intersecting lines. And let's remind ourselves how that one occurs. Here we actually need the double cone to really see both pieces of the hyperbola. It's a terrible picture. But here the slice is going to be more steep. So I'm going to go ahead and try and make that more steep right there. More steep. And then we see that hyperbola cuts in there, and that another branch up here. Almost, it looks a little parabola-like, but it's not. And remember, these cones extend down forever in the true conic section fashion. And then the last one is just a circle, which occurs, as everyone I'm sure recalls, when it's exactly parallel to the base. And that's when we get our circle. And really, circle, most people feel like that should just describe that as a special case of the ellipse, which it is. So you could actually think of this as there's really 3 conic section families: parabola, ellipse, hyperbola. This is same slope, less steep, more steep, and a circle is just a special case of that guy.